Alright, so let's, for the moment, consider Cantor's diagonal argument. Okay. So, here's a restatement of it. T is the set of all infinite sequences of binary digits, 0 and 1. S1, S2, S3, etc., all the way through, is an enumeration of all elements of T. Okay? An element S of T can be constructed that is not within the enumeration. S is constructed by taking the kth term of Sk, inverting it, so if it was 0 it goes to 1, if it was 1 it goes to 0, and using that as the kth term of S. So if S1 starts with 0, S starts with 1. Okay. Since this yields an element S of T which did not exist within T, we get a contradiction. This contradiction is attributed by Cantor to derive from the assumption that T is enumerable. So he concludes that T is not enumerable as a resolution to his paradox. Okay, that's Cantor's diagonal argument. But it is worth noting that neither Cantor nor anyone else whose commentary is easily found ever questioned the validity of the proposed construction of S as genuinely yielding an element of T which was not contained within the enumeration of elements of T. Okay. Notably, this reduces to the Archimedean property, since we can order our enumeration of elements of T such that S would naturally come at the end of the enumeration sequence, and all of its digits would all be 1s. Thus we start with S1 being a string of all zeros, S2 would be all zeros save for its final digit, but note that S2 is an infinite sequence, so it has no final digit. And then S3 would be all zeros save for its penultimate digit, but again S3 is an infinite sequence of binary digits, so it has no last two digits. And worse, if we proceed in this manner, there would be a sequence between S3 and S4, wherein the last two digits are 1. That is, the space between S3 and S4 can be divided, since an infinite string of zeros that ends in 0011 falls between S3, which is an infinite string of zeros that ends in 0010, and S4, which is an infinite string of zeros which ends in 0100. So ironically, the goal of demonstrating that T is not enumerable doesn't even require us to consider whether S is within T or not. We can assert that it is, and still arrive at the conclusion that T is not enumerable. But note that this conclusion requires us to talk about the final digits of infinite sequences, which is nonsense, but notably also something which the original diagonal argument does implicitly with both the size of T and the assumption that S is actually constructible. Right? In order to construct S, you have to be able to get to the end. In order to have a size for T, you have to be able to get to the end. So the original construction is doing this same thing, it's just doing it in different places than where we're doing it. I just moved where we're doing it. Okay? So what we have now is a proof by contradiction that Cantor's diagonal argument, which is itself a proof by contradiction, cannot be correct. And this is also a direct result of Cantor's diagonal argument. That is, Cantor's diagonal argument contradicts itself. So nobody should accept it. Okay, now let's move into why multiplication breaks set theory, sort of Mello-Frankel set theory. Okay? So I've noted before that Pressburger arithmetic was formulated specifically to avoid the paradoxes which multiplication induces in Peano arithmetic. And further, that Godel's incompleteness theorems are just a demonstration that these paradoxes are unavoidable if Peano arithmetic in its entirety is used. And of course keep in mind that ZF or ZFC uses Peano arithmetic. Right? We can interpret the problem with multiplication quite simply. Peano's axioms establish a discrete number system via the successor function. That is, the numbers start at 0 and grow in discrete steps of 1. Thus 1 is the successor to 0, 2 is the successor to 1, 3 is the successor to 2, etc. And 0 itself is not the successor to anything. This is claimed to be built from an addition operator, and definitions of 0 and 1. It might be noted at this point that 1 plus 2, or 1 plus 1 equals 2, is in fact implicitly defined by the formulation of the successor function. And if this implicit definition is not understood and accepted by the intended audience of the publication, then 2 plus 1 equals 3, 3 plus 1 equals 4, etc. are not actually derivable from it. You need the demonstration that 1 plus 1 equals 2 in order to be able to get to any other numbers. Okay? And it would thus not accomplish what it's claimed to accomplish. But this isn't what we're concerned about at this moment. Okay, already we have a major problem though, since we can reverse, where the hell? Scrolling too fast. Since we can reverse the addition operator to yield subtraction. We can construct negative numbers from the numbers thus far defined by the successor function, and go from having the set of whole numbers to having the set of integers. However, it should be noted that negative 1 plus 1 equals 0, and thus 0 is the successor to negative 1, despite the foundational axiom that 0 is not the successor to anything. But apparently nobody cares about this paradox. So now let's extend things by throwing in multiplication. This should be a very odd thing to do, since multiplication is simply iterated addition, and we already have addition. So adding multiplication shouldn't do anything, right? Well, the problem comes when we reverse the multiplication operation, since this yields fractions. Thus, adding multiplication takes us from having the set of integers to having the set of rationals. But now we have values falling between 0 and 1, which violates the axiomatic claim that 1 is the unique successor to 0. And again, apparently nobody cares about this paradox. At this point, we can see how the Archimedean property plays into things. If 1/2 is a more valid successor to 0 than 1, then 1/3 is a more valid successor to 0 than 1/2, etc. So the true successor to 0 is 1 on n, where n is the final number generated by Peano's successor function. But the Archimedean property itself literally tells us that because of the existence of multiplication, no such number can possibly exist. Cantor's diagonal argument can now be brought back into consideration. If we interpret the elements of t to indicate values between 0 and 1, with S1 being a string composed entirely of zeros, indicating 0, and S, which is a string composed entirely of 1s, indicating 1, then we can see that the existence of some string between S2 and S3 is simply a restatement of the Archimedean property. However, as already demonstrated by considering Cantor's diagonal argument from a different perspective than Cantor himself did, all we've really shown is that infinite structures cannot be enumerable. And this really shouldn't come as a surprise, since that's what infinite fucking means in the first place. In means not, and finite means end. So infinite means not never ending. So anything which is properly infinite cannot be completely analyzed by any process which deals with it in discrete chunks. Now take all of this and reconsider the incompleteness theorems. They employ diagonal arguments regarding infinite sets to show that any set-theoretic approach which includes Peano arithmetic cannot be complete. That incompleteness compelled the invention of Pressburger arithmetic prior to the proof of the incompleteness theorems, which in itself already indicates that the problem is probably with the notion of a multiplication operator within the context of Peano's axioms. But now we've seen conclusively that it is definitely the introduction of an explicit multiplication operator to Peano's axioms which causes the fault. And thus the problem is that Peano's axioms themselves are wrongly formulated. So of course any foundation of mathematics which incorporates Peano's axioms, like Zermelo-Fraenkel set theory, will also be wrongly formulated.